We move to estimating a population mean with a confidence interval. Previous material has shown you how to estimate a population proportion. Now we need to talk about the mean. If you recall, confidence intervals are always of the form point estimate plus or minus margin of error. For proportions, we specifically ended up with the following formula. P hat plus or minus z alpha over 2 times the square root of p hat times 1 minus p hat over n. Okay, so let's recall what each one of these things are. So remember, this is our sample proportion, the best possible point estimate, or p, which is what we're trying to estimate. This is our critical value. And just as a reminder, we have the standard deviation of sampling distribution of p hat, if you recall, was square root of p times 1 minus p over n. This would be the most logical thing to place here in this spot, but you'll notice that these have p hats instead of p's. That's because we're trying to estimate the population proportion p, so there's no way we actually have that value. So we used p hat as a direct replacement for that, and that's why we ended up with this as a result. I just wanted to point that out because it isn't exactly the standard deviation of the sampling distribution of p hat, but it is a replacement for it, which we use in order to calculate our problems. And you're going to find that there's some consistency with now moving to means. Speaking of, why don't we jump right into that? What about a confidence interval in which we're trying to estimate a population mean? What does that look like in terms of a formula? Well, if we use the sample proportion p hat to estimate the population proportion p, it would make sense that if we're trying to estimate the population mean mu, then we should be using x bar, and that's exactly what it's going to be. So we're going to do the sample mean for that. Okay, a little plus or minus. On the left side, we are going to have a critical value again, except there's going to be a little bit of a change. I'll tackle that in 1 second. I want to go over to something that I can get through quicker, which is what about the standard deviation of the sampling distribution of x bar? So if you recall, that was sigma over root n. Now we're kind of in the same pickle we were before, where if you think about it, remember when we label distributions as normal, we usually label them normal mu sigma, right? That's because these guys pretty much go together as mean and standard deviation. And if we're trying to estimate mu that is unknown, then how is sigma known? Well, again, it doesn't make a lot of sense. So instead of using sigma, we're going to use its next best alternative, which is going to be s. So therefore, in the formula, this is going to end up being s over root n. All right, so let's talk about that critical value. So what I'm going to do is I am going to copy the z alpha over 2 down, but I don't want you to write that anywhere in notes as facts because it is untrue in terms of the formula. That's not the critical value we're going to be using. But I just want to prove a point while I'm actually, or discuss something while it's actually there. So statisticians actually did start using this formula way back when. And knowing that they were forced to use S here, they found that the results from sample to sample varied so much when it came to this sample standard deviation that the one standard normal distribution, which is the z-curve, was unable to accommodate such fluctuation. So they found that this interval was inaccurate more often than not. So what ended up happening is a famous statistician named William Gossett came around and created a new distribution called the student's t-distribution. The whole point of this t-distribution was it was more accommodating for the sample standard deviation. So why exactly is this t-curve so accommodating? Well, let's bring up Google Chrome here. I'm at desmos.com. It's an online graphing calculator. You might have used it in high school or in some other college math classes. I use it a lot in pre-calc and calculus to graph crazy functions. There's not really a lot like that in statistics, so we only really use it for this, or I only use it for this. So what I want you to do is don't focus too much of what's going on the left side of the page. Focus for now on the right on the graph. The red curve is the standard normal distribution graphed perfectly and accurately. We're going to use that as a guide for us so you can compare the t-distribution curve, which is the blue curve, to the z. So the t is basically going to move, whereas the z, the red curve, is not. So the z curve is stable because there's only one of them. You can't change it. So we're going to focus more on the t-distribution curve, which is the blue one. Now, why is the t-distribution so accommodating? Because there is a different one for every sample size. So if you look over on the left side of the page just for a second, the only thing you have to concentrate on is the lowest value where it says n equals 2. So what does that mean? That means this on the right side this blue curve is the t-distribution for n equals 2. Okay, so a couple things to take note of. First, the t-curve is centered at 0, just like the z-curve is. You can see they're symmetric about the origin, no difference. Another similarity, they both have an area of 1 underneath them. Why is that so relevant in terms of explaining that to a student? Well, you can see that on the left and right side of the graphs, the blue curve is higher than the red curve, or farther away from the axis. Whereas in the middle of the graph, the red curve, the z, is actually farther away. So that means there's a difference in where the area is stored in each of the curves. So we would say that a t-curve has more area in its tails, the left and the right, than it does in the center, whereas the z-curve, our standard normal curve, has more area in the middle, in the center of the graph. That is a very important observation. So what if we went over, so I'm going to go over to the left side here, and I'm going to put my finger on n equals 2 thing here, and I'm going to move this around. So look at the graph. So I'm going to start at 2. I'm just going to move it this way to 5. So what happened in going from 2 to 5? It looks like the area in the t-curve moved from the tails more into the center. As you saw, the center sort of creep its way more up to the z-curve. And as you keep on doing that, increasing it and watching the curve as it goes, keep watching the curve, it seems that it's basically at these higher sample sizes getting closer and closer to a normal distribution. And it does turn out that at the highest values of sample size for a t-distribution, it almost perfectly becomes a standard normal distribution. So it actually turns out that if we were to go back to here and put a z here, this actually would work okay for large sample sizes because the two curves basically are one and the same at these large sample sizes. But If we go down to smaller sample sizes, it turns out that the z just doesn't accommodate what this sample standard deviation, how much it varies. So that means that's why we use a t-curve, which has a different distribution of areas, specifically more areas in the tail. For each sample size, it'll be able to fluctuate and accommodate that varying sample standard deviation. Okay, so I did mention that there was a unique t-curve at every sample size. We saw that on the graph, right? I was moving the slider over and over and the curve was changing, blah, 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 right? So it turns out that even though that's true, we don't actually refer to a t-curve by its sample size. We refer to it by something else. If you look at the t-table real quick, just a reminder, remember the bottom row of this were all your z critical values that you were computing for your proportion intervals. If you look towards the top of the curve, you'll notice there is no value of n anywhere. So you would think it would be there if we wanted to refer to a curve by its sample size. Well, instead, we have this very patriotic term over here called the degrees of freedom. The degrees of freedom is abbreviated by the symbolism df, and it is equal to n minus 1. So for example, if you look at this curve I have right here, this is actually an n equals 14 t-curve, specifically. So if I were to go over here and just put 14 into this little thing here, that would be that curve. So I have copied that over to here, and that's what it looks like. But again, we don't refer to it as an n equals 14 curve. We actually refer to it as its degrees of freedom. So degrees of freedom is equal to n minus 1, which is equal to 14 minus 1, which is equal to 13. So we would call this a df equals 13 t-curve. And to be clear, we use this t-curve at 13 degrees of freedom because it's the most accurate way to compute a confidence interval for a population mean when the sample size is 14. So let's now focus on the formula above. So this is our formula right here, right? This is our confidence interval in estimating the population mean. In most problems, you're going to be given or can calculate x bar or s, n will provided. So the only thing similar to our proportion interval, the key is being able to compute our critical value. So we're going to have to find T alpha over 2. Suppose, for argument's sake, that our alpha over 2 is 0.05. So we need to figure out what our T sub 0.05 critical value would be, specifically at 13 degrees of freedom. So we go over to our T table, and again, what are we dealing with? We have to look up our upper tail area. Now, what did we do for our z alphas over 2 when we were dealing with our standard normal distribution? We worked our way all the way to the bottom, and we ended up highlighting the value that was associated with that column. That was our z sub alpha over 2 value for our standard normal distribution. We are no longer in the standard normal distribution. We are in a t-curve at 13 degrees of freedom. So therefore, what do? We go over to the side here, and we find that 1.771 is the value we need for our critical value. So if we were doing a confidence interval this second, that's the value that would go in for that critical value. Before we move on with the formula and start learning a little bit more how to use it, I do want to mention a couple things from the table. If you look down at the bottom degrees of freedom values down here, you'll notice that they start skipping around. The reason why they skip around is because, as we mentioned, right, when we were looking at this table, at higher degrees of freedoms, really there's not as much a difference between the curves. They look very similar, as opposed to at they're smaller, they are very different. So the rule of thumb is that if you get a value, let's say I told you that the degrees of freedom was 46, right? Usually, just so that everybody's on the same page and we're all doing the same thing in terms of the results, I usually have you round down to the next value. So if it's 46, you would use 40. If it was 98, even though it's right next to 100, you would use 90 and so forth. If we all sort of stick to that, then everyone sort of gets the same answer, which is very convenient for me. The other important fact here is I just want you to look at the last lines here. So we know that in a normal curve, standard normal curve, these are going to be our critical values. But if you look at the critical values that are basically right above it, right? These guys, all of these guys, you can see that there's not a huge difference between the values that are right above them and the values themselves. I mean, even down here, they're almost identical. Here you go here, and there's another couple that are identical. So, again, that is just further proof that as the T curve is at higher sample sizes and degrees of freedom, it basically just becomes a standard normal distribution. Okay, just a few things to clean up here. So remember that in a confidence interval to estimate the population mean, this is E. So similar to our previous proportion interval, this was E. So now the margin of error has changed. Also, there are new requirements for this. So if you recall, the requirements for our proportion interval were an SRS, and we had to make sure that n times p hat times 1 minus p hat was greater than or equal to 10, which is the majority case that we used. But there was also that little n less than or equal to 0.05 times big N that we would use if it's a really small population. We don't usually do that, so we're not going to use that a lot. But those were the requirements. So it turns out that most of those requirements are the same, but we have to sort of mimic the sampling distribution of the sample mean a little bit more. So first, yes, we absolutely need a simple random sample. That's going to be pretty much the case in any of these inference procedures. But we don't have N's and P's when it comes to determining normality. So your memories, hopefully, they work pretty well here. Remember when we were doing sampling distributions, the key is that we needed a sample size greater than or equal to 30 to ensure normality. And that is pretty much the standard across the board. And once again, this is for large populations. Just be careful though, same as last time, if you have a small population, very small, we want to make sure that little n is less than or equal to 0.05 of big N. So basically, we don't want the sample to be greater than 5% of the population. But again, we just don't use this that much. We just want to sort of keep it in the back of our heads. The overwhelming majority of the time, you're going to be dealing with n greater than or equal to 30 as our requirement for this. And just the last thing on this, when it comes to Z distributions, they are not very flexible. Z distributions need that sample size to be greater than or equal to 30 to ensure the sampling distribution is normally distributed. But it turns out with T-curves that there are some distributions that can be normal as long as there's no major outliers. We don't get into that much detail in this course, but it's something just to take note of going forward. We often refer to T-curves as being, or T-distributions as being robust, just because they can handle a little bit more because of the fact that the curve is fluctuating per every degree of freedom that you change it to. All right, let's head on to the examples here. It says in a class survey, students are asked how many hours they sleep per night In a random sample of 30 students, the mean was 5.77 hours with a standard deviation of 1.572. Compute and interpret a 98% confidence interval for the true mean amount of sleep. Please verify assumptions. Right away, you can see that they're looking for a confidence interval for the true mean. So we are in the world of estimating a population mean using a confidence interval. So remember, what does that formula look like? We got x bar plus or minus t alpha over 2 times s over root n. Quickly testing the accuracy of this interval. Remember, the requirements are we need a random sample, which you can see right here. And we have a sample size right here, which is equal to 30. So that means we are good to go there. It appears for our problem that we have our mean here, we have our standard deviation here, and we have n here. So that should work, fill in these quite nicely, and we can do that in a second. But remember, in order to find t sub alpha over 2, we need to find alpha. So that is where our 98% comes in. So recall that alpha is always equal to 1 minus the decimal equivalent of our confidence level, 0.98, which is 0.02. We want alpha over 2, which is going to give us 0.02 divided by 2, which is 0.01. So basically, this right here, this whole thing is 0.01. If we were doing some type of z interval, that would have been enough, because there's only one. But because there are many t-curves, we of course need that degrees of freedom in order to locate the proper value on our table. So remember, degrees of freedom is equal to n minus 1. Our n is 30, so 30 minus 1 is going to give us 29. So all we must do is go to our t-table. We want to find our value 0.01 for the upper tail area, and we want that at 29 degrees of freedom. So that's going to put us at 2.462. So we know this is going to be that. Just filling in the rest of this, we got our x bar, which is 5.770. We have our standard deviation, which is 1.572, and the square root of our sample size 30. Just be really careful here. The most common mistake is students will put 29 instead. But remember, that is back to being the sample size. Now remember, this entire thing is our margin of error E. We want to compute that right off the bat. So if you throw that in your calculator, you're going to get around 0.707 as your margin of error. All right, so that means we're looking to do 5.770 minus 0.707 on the low end of the interval, and 5.770 plus 0.707 on the high end. If we do a little bit of computations there, we're going to get about 5.063 and about 6.477 as our interval. Okay, I just paused it right there so I could write this in for you. So here's your interpret part, whereas this right here is the compute part. The interpret part is coming. We are 98% confident that the true mean amount of sleep for students is between 5.063 and 6.477 hours. Okay, the big difference here, only difference, is that with proportions, there's never a label. Whereas with a mean amount of something, there usually is a label, so you just want to make sure here that you include that. All right, let's take a look at the big picture here to make sure there's full understanding. Remember, we want to know the true mean amount of sleep by all students. In other words, mu. We don't want to go out and ask every single student on the planet how much they sleep. Too expensive, too much, right? So we don't know what mu is. So what do? We go out and we take a sample and we estimate what mu is using a confidence interval. So right now, we are 98% confident that the true mean amount of sleep by students falls in that range right there. Now note also that if we had 100 samples, 98 of them would produce intervals that do contain the true mean amount of sleep because we're in 98% confidence. But 2 wouldn't. Do we know that this value is one of the 98 correct ones or 2 incorrect ones? No, we don't. I know that sounds crazy, but we don't know that. That's also why you often see many intervals and many different samples taken to get a better idea of where that value might fall for the true mean amount of sleep. Okay, let's do another example. It says a random sample of taxicabs had the following consumption of gasoline in gallons on a particular day. Given that the population is approximately normal, compute and interpret a 90% confidence interval for the mean daily use of gasoline by all taxicabs. Please verify assumption. So again, it appears that we're doing a confidence interval for a mean. So we immediately can bring our formula to the forefront. Okay, we have some requirements to test. It looks like we have a random sample, so that's good. But you'll notice that we only have 7 in our sample. So normally that would probably not be good enough. But you'll notice that they did say that the population was normal. So if you recall from our sampling distributions of sample means, if the population was normal, it didn't matter what the sample size was. So we're good. But population is normal. So good to go. Okay, so if you recall, our next step is to figure out our critical value situation. So we need an alpha. So we have a 90% confidence, so 1 minus the decimal equivalent of the confidence gives you 0.10. So alpha over 2 is going to be taking that 0.10 and dividing by 2 and getting 0.05. We also are dealing with a t-distribution, which means our degrees of freedom is going to be equal to n minus 1. So we're going to take our 7 minus 1, and we're going to get a 6. So basically a df equals 6t curve is what's going to fit this distribution the best. Now, if you remember in our previous problem, we immediately started throwing in our values of x bar, s, and n, right? Well, it turns out we're only given one of those things, n. We know n is 7. Great. But curiously, there is no x bar and s that is actually given in the problem. Why? Because they gave you the data instead. This is very much a real-world application because most statistical studies, you're going to get the data instead. So what do? Well, you use software. You use a calculator, among many other things. X-bar, pretty easy. You could do that by hand. You can easily do it on a calculator. If you do so, you are going to get x-bar is equal to 23. So make sure you're not writing mu there, right? X-bar is the sample mean. The standard deviation is a little bit different. The sample standard deviation is something we need, not as easy to just do by hand, so to speak. It'll take a while. So you might note that in homework problems, they might direct you to use StatCrunch in order to calculate it. But there are several online calculators. You can just Google it and write, standard sample standard deviation online calculator. You can just plug in the numbers and get them. Of course, on an exam situation, that means that I would have to give you the sample standard deviation, and that would probably look something like this. So I hid it for now because I wanted to do the big surprise, but I would probably give it to you. So it's 5.42. But in the homework, probably not. I want you to work on figuring out to do that stuff on your own. Okay, so we can now start throwing in these numbers. So we got 23 plus or minus. We'll take care of the critical value in a second. This is going to be 5.42 divided by the square root of, remember, it's 7 and not 6. Be careful with that. Our critical value. So what are we looking for? We're looking for t sub 0.05. T sub 0.05 at 6 degrees of freedom. All right, so t sub 0.05 is here. We got 6 degrees of freedom here. It looks like we're going to end up at 1.943. Okay, of course, this is our margin of error. So we're going to compute that margin of error, and that'll end up being, it looks like 3.8. 3.98. So therefore, what are we trying to do? We're trying to do 23 minus 3.98 for our low end and 23 plus 3.98 on our high end. And that is going to give us 19.02 to 26.98. And finally, we have our interpret portion of the proceedings. We are 90% confident that the true mean daily gasoline consumed by taxicabs is between 19.02 and 26.98 gallons. So remember your label there. Okay, so the final topic in this section is the same as the final topic in the previous section. So if you recall, when we were estimating a population proportion, there were times where we really needed the margin of error and confidence level to stay the same. So therefore, we were tasked with finding the desired sample size in order to get that done. So desired sample size. How did we accomplish that? Well, we found, first of all, we took the margin of error and we solved for n. Well, right now, as far as we know, so let's highlight it here, this is our margin of error. So let's take a peek at that. E equals T alpha over 2 times S over root n. Okay, so there is one issue with this formula. We'd love to use it, but there's something that's blocking us from doing so. What exactly is that? Well, we know that we're going to be, first of all, we know what we're solving for. It's n. Okay. We know that we're going to get a standard deviation from somewhere. It could be a previous study. It could be that, whatever it's going to be. We're going to get a standard deviation. We know that we have some margin of error that we need to maintain. That's the point of this. We also know we have some confidence level we need to maintain that will lead us to this critical value. So, what's the issue? Well, in order to find any t critical value, we need to know its degrees of freedom for the curve it's associated with. And in order to find the degrees of freedom, we need to know the sample size. That's a problem, because what are we trying to find? The sample size. Therefore, it just doesn't make any sense to use t in this problem. So as a simple substitute, statisticians decided to replace t with its buddy z and work on desired sample sizes with this formula. So let's start solving. First thing I'm going to do is just organize terms a little bit. I'm going to throw this z alpha over 2 on the top with our standard deviation in our numerator over root n. Once we have that, then all we have to do to clear fractions here is to multiply both sides by root n. That is going to give us e root n equals z alpha over 2 times s. Moving up here, remember we're still trying to isolate our value of n, our sample size. So we're going to have to get rid of our e. So we're going to divide both sides by e here. So that's going to give us root n is equal to z alpha over 2 times s all over e. And then finally, in order to accomplish this, we're going to have to, and get rid of that radical, we're going to have to square both sides. So we're going to end up with our sample size being z alpha over 2 times s all over the margin of error squared. Desired sample size problem for me. Here's our example. An athletic trainer wants to determine how large a sample should be taken to be 99% confident that he will estimate the true mean healing time in an ACL tear to within 3 weeks or less. Records of past patients has a standard deviation of 3.55 weeks. All right, here we go with the formula. So n is always going to be equal to our z alpha over 2 times our standard deviation over our margin of error squared. Okay, we do have some of these values, but right now we don't have z alpha over 2. We do have 99%. which means life is a little bit easier. We don't have to worry about degrees of freedom, but we still have to do our calculation. Alpha is equal to 1 minus the decimal equivalent of the confidence. That's 0.01, which means alpha over 2 is going to be 0.01 over 2, which is going to be 0.005. So this value right here is basically z sub 0.005. That's much easier to find because all the z values were back at the bottom of the table. So we just have to find our fourth to right column over there. Our z will be 2.576. So 2.576 here. Standard deviation of past records, it looked like was 3.55. And our margin of error says within 3 weeks or less. A lot of times the word within, because plus or minus, simplifies or signifies your margin of error. Not always, but it does come up that way a lot in problems. So therefore, if we do the mathematics here, we're going to end up with, looks like 9.29. Just be really careful. Most common mistake is forgetting to square this value. Now, remember the review portion of this. 9.29 is not the answer. Why is it not the answer? Because you can't have 0.29, a fraction of a patient. And in order to ensure that we have this margin of error at this confidence, we must get to 9.29. So the only way to make sure we get it is to go up. Always round up. So therefore, we are going to take a sample of n equals 10 patients.